Welcome to this lesson on Introduction and Basics Cycle. In this video, we'll uncover the basic principles that explain how cooling works in HVAC systems, from the purpose of refrigeration to the core components of the cycle, and their real-world applications. This lesson will provide the essential knowledge you need to understand how refrigeration enables thermal comfort in buildings. In this video, we'll start by exploring the purpose of refrigeration, understanding why heat needs to be removed and how this process supports thermal comfort and preservation. Then we'll introduce the vapor compression refrigeration cycle, focusing on its four core components and the way they work together to absorb and reject heat. Finally, we'll see typical HVAC applications that rely on this cycle, from room air conditioners to central chilled water systems, highlighting its central role in the cooling strategies used across the industry. By the end of this video, you'll have a strong foundation to build on as we move into deeper thermodynamic and design topics in the following lessons. In this lesson, you'll gain a foundational understanding of how vapor compression refrigeration works. By the end of this video, you'll be able to describe the basic components of the cycle and understand how each one contributes to the refrigeration process. Have you ever stopped to think about what happens inside an HVAC system to keep an entire building cool, even on scorching summer day? Take a moment. Try to imagine the journey of heat as it's removed from your room. What kind of technology makes that possible? Behind this process lies a powerful thermodynamic cycle, one that operates quietly in the background of our daily lives. Vapor compression refrigeration. Refrigeration is the process by which heat is removed from a space or a substance, lowering its temperature or regulating conditions. It plays a vital role in many aspects of modern life. At its core, refrigeration removes heat to lower temperature. Whether from air, water, or stored items, this cooling effect is the foundation of the entire process. It has widespread applications in food preservation, climate control, and industrial processes, from keeping milk fresh to enabling air conditioning, to supporting pharmaceutical production. Refrigeration is everywhere. And in the HVAC industry, refrigeration is the method by which indoor heat is extracted and rejected to the outside. This is how we achieve thermal comfort in homes, offices, and other buildings, especially during hot weather. The vapor compression refrigeration cycle is what makes all of this possible. It's a quiet, powerful engine at the heart of the most modern cooling systems. The vapor compression refrigeration cycle consists of four essential components that work together in a continuous loop to move heat from one place to another. First, we have the evaporator. Here, the refrigerant, typically a low-pressure, low-temperature liquid, absorbs heat from the surrounding environment and evaporates. This process cools the air or substance in contact with the evaporator. The now vaporized refrigerant moves into the compressor, where it is compressed to a higher pressure and temperature. This step requires energy input and is what enables the refrigerant to later reject heat. Next, the high pressure vapor enters the condenser, usually located outside the cool space. Here it releases the absorbed heat to the surroundings and condenses back into a liquid state. Finally, the refrigerant passes through the suction device, where its pressure and temperature drop suddenly. This prepares to re-enter the evaporator and begin the cycle again. This simple yet powerful sequence of phase changes and energy transfers forms the core of most modern cooling technologies. Vapor compressor systems are found in room air conditioners, including both split and window units. These are common in residential and small commercial applications. They also power packaged rooftop HVAC systems, which are often used to serve large open plan spaces in commercial buildings. In central chilled water systems, large-scale compressors chill water that is then distributed to air handling units throughout a facility. Variable refrigerant flow systems use vapor compression to deliver flexible and efficient climate control across multiple zones within a building. Finally, heat pumps, which can reverse the cycle to provide both heating and cooling, are increasingly popular in sustainable and all-electric building strategies. The vapor compression cycle is the driving mechanism behind most cooling systems used in HVAC. It forms the backbone of modern cooling, operating at the core of technologies that control indoor environments. At its heart, it works by removing heat to lower temperature, making living and working spaces comfortable even during extreme weather. The cycle relies on four essential components: evaporator, compressor, condenser, and expansion device, each playing a specific role in transferring heat. It's supplied in various HVAC systems, including air conditioners, chillers, and heat pumps, making it a versatile solution for different building types and climates. By enabling thermal comfort through continuous phase change and energy transfer, the vapor compression cycle supports efficient, reliable, and scalable cooling solutions. In the next video, we'll explore the thermodynamics behind the cycle, learning how to represent it on the TS and PS diagrams, and how to evaluate its efficiency using the coefficient of performance, or COP. After that, we'll take a closer look at refrigerants, the working fluids in the cycle. We'll compare their thermodynamic properties, safety classifications, and environmental impact, including ozone depletion and global warming potential. Finally, we'll examine real system behavior and explore how to improve performance using enhancements like subcooling, superheating, and smart controls. Each step deepens your understanding of how these systems function and how they are optimized in the HVAC industry. Let's continue your journey.